welcome to lecture 16. So, today we will try to integrate declarations within a command language and see how to manage both aspects. Let us go back briefly to what we said about ML like programs. Their environments were variable value bindings, and when you have a command language, you are required to have something which allows changes to be reversible and something else that allows changes to be irreversible, and as a result we require stores in addition to environments. The relationship between the two will be that the stores will depend upon the actual bindings created by environments, and you can only have stores for given environments. Yeah. And so, as I said, there is something implicit about an imperative programming language, in which there is an implicit assumption about the existence of memory, and the fact that therefore memory can be updated requires the use of locations. So, and these locations are intermediate between a variable and its value. So, as opposed to constants which would be just identifier value bindings, variables would be identifier location bindings, and further we would have values associated with locations, which loosely speaking refer to values contained in locations, and the targets of assignments would be locations and the sources of assignments would be values, right. So, for any given environment, a store would just be a finite set of location value associations, and these are sort of an inevitable consequence of imperative language programming, right. So, and going quickly through it, we will assume that we will have environments created by declarations and stores will be updated by commands. And in the case of the most important command which actually allows the updation of stores is the assignment statement, or either explicit or in some implicit form, which has a target and a source, and we have and the target actually refers to some location and the source actually refers to a value contained in a location, even though we use the same name for both. In the context, depending on the context, you will either take the L value or the R value. So, let us look at the language today. So, I will just take this very simple language. It's so we have an expression language consisting of, well, numerals, identifiers and binary operations. For the present, I will assume that these binary operations are fully defined. None of them is it's not a partial operation. We have the usual booleans maybe, and we have declarations. So, like in the case of the PL0 language, we have constant declarations, we also have variable declarations. In this particular case, you can see that since our only data type at the moment are integers, it is not necessary to actually define a type here. So, it's enough to just have a declaration like this, and of course we could sequentially compose declarations. And then our commands are the usual commands: assignment, sequential composition, maybe conditional, while, whatever. But more importantly, we also have blocks. Yeah. So, this is how, informally you could look upon this as just declarations followed by commands, but if you okay, so this language is sort of slightly, it's not exactly like PL0, because for example in this language, well, every identifier in a declaration is preceded by a reserved word, constant or var, and then the way we have defined the BNF, there is nothing which says that all constant declarations should precede all variable declarations. So this seems to suggest that you could actually mix variable and constant declarations. Okay. So which does not seriously affect the meaning of the language. For example, you could, if we follow, so constant and variable declarations may occur in any order and may be interspersed. Okay, but if you follow the principle that declaration always precedes use, then it does not really matter, because since all the variables are uninitialized, in a constant declaration you cannot have any occurrence of a variable declared just before it, right. So the restriction that all constant declarations should precede variable declarations is just a pragmatic restriction, and would not really affect much. And since variables are uninitialized, the constant declarations also do not interfere with the variable declarations. Okay. So it really is useful only in grouping together the same kind of declarations into one entity and separating out different kinds of declarations for readability, for parsing maybe, but otherwise it has no semantic sanctity, right. So but anyway, we will use this this basic feature that declaration always precedes use. So if you were to look at PL0, if you were to actually give a BNF for the PL0 kind of declarations, then what we would have to do is we would have to have a classification like this, where according to those rules you need not have a declaration at all. For one thing, you could have just a just a sequence of constant declarations, just a sequence of variable declarations, or a sequence of constant declarations followed by variable declarations. So I have introduced two new non-terminal symbols, DC and DV, for constant declarations and variable declarations, and you could for example the PL0 kind of constant declarations, the variable declarations could be written out in extended BNF like this. So if the reserved word constant occurs, then there has to be at least one constant declaration followed by 0 or more occurrences of other constant declarations separated by commas, and similarly with variable declarations. Of course, you do not need to have any declaration at all, right. So and as far as blocks are concerned, the important thing is that blocks are really like unnamed or anonymous procedures, right. And as a result, what it means is that the question of naming is actually very important in any kind of programming. If you have an unnamed block, then what it means is that it cannot be called from anywhere, right. So which means that it is a purely local block, and therefore if there were any declarations, they are purely local to that part of the block. So in the BNF I have put in this pair of braces here, to emphasize the fact that supposing you intersperse declarations and commands, then you cannot arbitrarily intersperse them, because declarations create environments, little environments, and commands update stores given the current environments, and these braces indicate actually the scope of a declaration, right. So this is, so the whole point is that you shouldn't be arbitrarily mixing up declarations and commands. If you did arbitrarily mix up declarations and commands such that a declaration is available throughout that command and you did not have these braces, then that is equivalent to moving all the declarations up to one place and separating out the declarations from the commands, which is a cleaner, which would be a cleaner design. So the idea is that if you were to actually intersperse declarations with commands, then you really want to have some extra local declarations, and therefore you want to create a new block, not otherwise, right. So which means that you have to clearly delimit the scope of those declarations that you intersperse in between. Yeah. So this is really like an unnamed procedure, and therefore what it allows, for example, is that it allows you to, so the declarations are purely local to the scope within which they are within which they occur, and they cannot be called from elsewhere. You can nest blocks in this fashion, because a block is just a command by whatever you, the braces act like a begin and an end, and so these blocks are really like algol 60 blocks. I mean, you could have local declarations within a begin and an end, right. So you could nest blocks if you like, and these braces really have no role to play, except that they clearly delimit the scope of the declarations contained within them. Yeah. And so what happens is that, so now let's look at the semantic definitions in such a setting. So as usual, we will have, so instead of a state, we are going to have a collection of, so let's look at the environments. Okay, let's look at the notion of locations. So we will, so in any kind of semantic definition, we of course assume that as in the meaning of the language is really independent on the bounds of resources that are available for the implementation of the language. So one thing is that we assume that there is an infinite collection of locations, right, and these locations are all may all contain some values, right. However, at any time in the execution of a program, at any instant in its runtime behavior, you require only a finite number of locations. There are only going to be a finite number of locations used by a program. So what should be available is an inexhaustible supply of memory, but at any instant of time in the execution of a program, only a finite amount of memory is actually being used. It might dynamically vary the amount, but always only a finite amount. So for any finite set of locations, we will define stores on that set to be the collection of all location value associations, right. So given a finite set L, the set of all possible values that may be associated with each location is a store at any instant, and the set of all stores is the set of all possible such mappings that you can draw, right, and this stores is of course parameterized by the finite set of locations that you are considering at the moment, right. So, and of course, as usual, stores are just so the set of all possible stores is just a disjoint union of the set of stores for all for each finite subset of locations, right. Now, right, yeah. So this is our notion of locations, and this is our notion of stores, right. So then let's look at the notion of environments. So now we have our language is such that it has both constant declarations and variable declarations, and the constant declarations in the language are exactly like the variable declarations in an ML like functional language. I mean, a variable in a functional language really denotes the name of a value that remains unchanged throughout a scope, and that property is fulfilled exactly by our constant declarations. What does change are the variable declarations. So an environment, again, part of the reason why but not all of it, the reason why there are only a finite number of locations used by a program is that it starts initially with only a finite number of identifiers, and therefore requires only a finite number of locations initially, and on demand more locations might be required, but always, unless it is an infinitely executing program, always there will be only a finite number of locations used, right. So, and an environment, so given a finite collection of identifiers, an environment is just a binding from identifiers to values or locations, and of course this plus here is a disjoint union. So which means that at any point you know whether a value comes from you know for any identifier in an environment, it means it is possible to determine whether it is a location or a value, right. Remember what I said about disjoint union, it's that if you take the disjoint union of two sets, firstly if there are two finite sets, then the disjoint union contains as many elements as the sum of the two sets, and each element also maintains an identity from which of the component sets it actually it is actually taken, right. So that's a disjoint union, and the set of all environments given a collection of identifiers. Yeah.
Sir, you had mentioned that the L value and the R value are interchangeable in the sense that the meanings are same. When we try to take the value, either we can take the L value or the R value. But
no, all that I said last time was that there seems to be some confusion between the L value and the R value. What I said a few minutes ago was that the same name is being used for both, to denote both L values and R values, and the context determines what we should take. It is not that you are allowed to take anything. Okay. What this further says is that your R values could also be locations. Right. So the matter is quite complex. It's not so simple. So the fact that locations could also be used as values, as storable values, means that locations could be R values themselves of certain expressions. Okay, and you require a dereferencing facility to find the R value of another R value which is actually an L value of some other expression. So the dereferencing operations in most languages, like C, you have a star which does dereferencing, or you have the circumflex in Pascal which does dereferencing. That only says that you can have an expression whose R value is actually a location, and if it is a location, then it means that you can actually look at its contents. So you can take the R value of an expression, but provided you ensure that you are taking things in a disjoint union fashion so that the identities are maintained. For example, you cannot look at the contents of a value of this form, but certainly you can look at the contents of a value of this form. And if these are going to be the storable values, then this process can go on ad infinitum. Right? All that I am saying is that the same notation is being used in most programming languages, and the context determines whether it's an L value or an R value. And secondly, R values could themselves be L values of some other objects. Right? So for the present, let's not get into the complexities of L values and R values. We'll just look at the simplest form, which is which occurs when you have a statement like this. When you have a statement like this for an identifier x, then this denotes the L value, which means the location, the identifier location binding. This denotes the R value, which means the value contained in the location to which the identifier x is bound, and so the context here determines when you should take an L value and when you should take an R value. So the context tells you whether if it occurs on the left hand side of the assignment, then you are actually talking about a location. If it occurs on the right hand side, then you are actually looking at the value inside a location. Yeah. Right. So the set of all environments is just again the disjoint summation of all possible kinds of environments. So there are some other. So for example, what many other languages allow is that declared variables are to be initialized in the declaration itself. This is to prevent uninitialized variables from being used or accessed or some such thing. Yeah. However, this is not always possible. For example, if you are declaring a large array in a language like Ada, then clearly it is not possible to initialize it at compile time. It is simpler to initialize the array by reading the values from a file through an explicit initialization, rather than to try to initialize it at declaration time itself. Okay, so so what this means is that variable declarations could in general modify the store. Now, as you elaborate a declaration, your environment changes, so the associated store also changes. In fact, you are moving from some stores L to another stores L prime as you elaborate a declaration. Further, even though your variables are uninitialized, we have to really talk about uninitialized variables as actually containing some value. After all, if your store is a function from locations to values, the moment a location has been created, that means there is a location to there is a value contained in it. Otherwise, your store's function is not really a function. Yeah. So one new condition we'll impose is that we'll add a new value which to the set n, right, and this value really denotes some undefinedness. It's an undefined value, and what happens with this value is, since it is just a value, we really have to look at its effect on the expression language. Supposing the undefined occurs, supposing there is an uninitialized variable in some expression, what is the value of that expression? So most languages would just tell you that it's, since it's an it's not, this is not absolutely essential. So for example, languages like Fortran, which do not require declarations of variables, actually take an initial value to be, if it is an integer variable, to be 0, if it is a real variable to be 0.0. So if you do not, if you have not initialized a variable, what happens is that very often it's assumed that it has an initial value of 0. So it's like an implicit initialization of the variable the moment it is encountered, right. However, that often complicates matters, both pragmatically and semantically, because firstly, if I have not initialized the variable, why should you assume that its value is 0 or its value is some identity element? That is firstly a point. The point is that even though your semantics assumes that there are an unbounded number of locations, pragmatically what you are going to do is you are going to reuse memory as and when it gets deallocated, you are going to reuse memory. And what can happen in that is that nobody is going to bother to do the housekeeping in memory that is deallocated, which means that that area of memory could have previously contained some values when it was previously used, and if you did not go through a fresh initialization, what could happen is that the old value might get used. So an uninitialized variable is something that is potentially hazardous. If you did not, so if it's safer to actually assign it a value that is clearly different from any of the workable values that you have, because if it already contains some value without your knowledge and it is actually being used, then it does not differentiate between an error of judgment on your part and a deliberate attempt not to initialize it, because you think that the initialization would be done automatically, right. So we will take the safe view that there is a new value which is there in the underlying virtual machine, but is not part of the language. It is not something that is realizable in the language. It is not something that a programmer can explicitly use. It is only in order to provide let us say a runtime or compile time error checking for uninitialized variables. Yeah. So the moment you take this attitude, then what happens is that all expressions which use uninitialized variables become meaningless. So the values associated with all expressions which use uninitialized variables are such that either they become stuck configurations or they lead to runtime error states, right. So this is what happens typically in Pascal. Let's say an uninitialized variable, very often it's even though it's easy to do it, most Pascal compilers do not actually check whether you have whether your variables are all initialized at compile time. However, at runtime they do point out that there was a variable without a value, and what that value is some kind of a null value which is assumed initially to be stored, right. So during allocation the Pascal runtime system actually cleans up that store, so that it does not contain some previous values, but this is not implemented properly in many compilers, and very often you will find that previous values that that location had would be used sometimes without any warning or an error message. So the Pascal language, of course, is clear that you have to uninitialized variables should be explicitly pointed out and should give a runtime error. So now, so the first thing is that before we get on to the actual semantics, the assumption of an unbounded number of locations means that every time a new variable is declared, you should be able to get a new location. Okay, if at any stage you have only a finite number of locations in use, then it's always possible to get a new location. So we'll define an implicit function for this purpose, which I'll call mu, which given any finite set of locations gives me a new location that is unused. Yeah. So pragmatically, if you can assume that the locations are all ordered by some ordering, then you can assume that nu is the nu of L gives you a location with the least location greater than whatever exists in L, for example, right. So we'll assume the existence of this function, which we'll use as a side condition. This function is absolutely essential because it is also useful when you are to do dynamic allocation of memory. For example, when you have pointer declarations, then you actually explicitly allocate and deallocate. It's also useful for implicit allocations and deallocations. So you could correspondingly define a delete, but then that's not essential. That's not essential in a semantic model which assumes an unbounded number of locations. Yeah, but delete is essential when you have only a finite number of locations, so that reuse is possible. Yeah. So we will look at the transition system. Now from now on we won't look at the complete transition system, we will look at only what modifications have to be made to the transition system, so that so as to be brief and clear about exactly what we are doing. So the transition systems are such that every expression, declaration and command, so every expression is evaluated in a given environment with a given store. So both the environment and store are parameters of our transition rules for all possible categories. Yeah. So we'll use so our typical expression transition system, for example, will look like this. We'll combine the two things the two concepts previously. So previously used. So for example, we will look upon any expression as being evaluated in this environment with this store. Yeah. Now the expression semantics, most of it can be rewritten in this form without much problem. The only thing that requires elaboration is possibly the difference between so what is the major change? The major change is that now you have two kinds of identifiers. They are either constant identifiers or variable identifiers. Otherwise, all expressions in our case, the expressions really depend upon are really the expressions that can occur on the right hand side of assignment statements. That's really the only kind of expressions that you have to you need to worry about, right. So the expressions that occur on the right hand side of assignment statements will all require their R values to be used. Okay, and the expressions and the only thing that can occur on the left hand side of an assignment statement in the case of this language are identifiers, variable identifiers, that is it, right. So let us just look at the expression semantics of in terms of just these two distinctions. So our basic, so I can, the expression axiom E naught is actually going to be split into two, right. So I will make it E naught 1 and E naught 2. So one thing is that if the identifier, so the value of this identifier is just a natural number m, provided the environment declares it to be a constant identifier. If the environmental binding for that identifier is the constant m, note that this m actually could be this undefined value too. Yeah, it won't be this undefined value in a constant declaration, because that undefined value is not explicitly available to the programmer except by some certain devious mechanisms like dividing some two previously declared constants by 0 or some such thing. So it's realizable in some strange ways, but it's not explicitly available to the user, right. So this m could be an undefined value, provided this tells you that if the environment associates with this identifier, note that we defined our environment as a mapping from identifiers to the disjoint union of values and locations. So which means that with every identifier is also associated its identity as to whether it denotes a value or a location. So if the environment associates a value with it, then the meaning of this expression is just the corresponding value in that environment. On the other hand, if the environment associates a location with it, then the meaning of this expression is that firstly there has to be this, so firstly the environment has to give the identifier a location binding, and if it gives it a location binding, then it is possible to look at the value inside that location binding, inside that location, and take that value. In either case, for an identifier that occurs just as an expression, which means that here I am assuming that within this language it only occurs as an expression on the right hand side of assignment statements, then for any identifier you have a corresponding value. Yeah, but there is a level of indirection if it is a variable, which is not there if it is a constant. Right. So the next thing, so the other ones, the expression language, as far as we are concerned, does not contain L values. In this simple language, it does not contain any L values. It contains only R values. So therefore, we have only these two cases to really consider. All other expression semantics will be more or less whatever we have done before. Yeah. So there is nothing much to the expression language. However, what we have to look at are variable declarations. So firstly, the constant declarations, there's no fuss to be made, because constant declarations are exactly like the ML variable declarations. Okay. So in an environment, a constant declaration of the form I equals E means that you evaluate the expression E, and then you create a little environment in which I is associated with that value, I is bound to that value, right, in that state, and there are no side effects in this language. So, so there is no, there are no other changes to be worried about. Yeah. However, in the case of a variable declaration, firstly what it means is that given a state, given a store sigma based on the set of locations L, given an environment already which has a collection ID of identifiers, when you encounter a new identifier, or it could even be an old identifier which is already present in this, then firstly what you do is you acquire a new location, and this new is very important in the sense that you are acquiring a location that has so far never been used. I mean, there is no confusion between this location and any other location that is present in L. Okay, this L has to be different from anything else that is present in this capital L. So you first acquire a new location and bind that identifier to that location, but that location has to have some well defined value, has to have a value which, so what happens is that your store gets altered. Your store, instead of being a function from capital L to values, becomes a function from capital L union this new small l to values, and you have to associate a value with this identifier. And since it's an uninitialized variable, you associate the undefined value with it. So, as part of a variable elaboration, your store actually changes. The store does not really get updated in the sense in which we normally talk about store updation, but what does happen is that the store gets extended to a new store where all the values of the old store are preserved, plus a new location has been added and therefore a new value to that location. Yeah. So, the other declaration rules are similar. So, you can take the sequential composition of declarations and create new environment store pairs. So, this declaration is, since the environment has got changed and the environment introduces new locations, therefore the store also gets changed in a certain fashion. Yeah. So, so I will assume that you can take the assignment statement semantics as before, except that now you have to take the assignment statement semantics as being of the form, if you have in a given environment row if in a given store sigma, if you have an expression E which, let us say, eventually goes to a value, let us call that M, and okay, since there are no side effects created by expressions, it is perfectly okay to consider the same L and ID here. Yeah. Then the effect of an assignment of the form I is assigned E in the state sigma L is to create a new store sigma L prime where sigma L prime equals sigma L with the updation that the location of the identifier I has associated with it the value m. Right. So the difference between, so here you are actually, this is actually a location. And not a, and nothing, and so in the case of an assignment this is clearly an L value. So you take the L value of this identifier, but throughout this expression you are only taking R values, right, and evaluate this expression in this store and this environment to eventually yield a value m and associate that value with this, right. So, so that is the only change in the assignment statement. All other commands remain more or less the same, except that we should now look at the block commands which have created new declarations. Yeah. So that is the only thing that is really new. So let us look at the block commands. Okay, or we will look at the block commands later. Thank you.